Hello to all attendees of AIM2022. I am Emanuel Nunez, Sardinha, PhD student at the University of West England, working currently at Bristol Robotics Lab. Today I will talk about our contribution paper, Embedding Soft Synergies into Soft Materials for Intrinsic Compliant Robotic Hand Grasping. Alright, the name is quite a mouthful, so let's break it down to get the structure of the presentation. First, relative to the soft synergies comes our motivation. We'll talk here about what are these soft synergies and why do we want to embed them. Next, for the soft material, it will be discussed in the methods on design, where we will discuss how to embed onto soft materials. And finally, of course, in results, we will see how this leads to the design of a hand. Right? Our core motivation is to try and improve the design of anthropomorphic hands. These are preferred to other designs, as it is agreed that by chasing for human-like designs, it is possible to capture some of its high dexterousness. Some common ways to capture this complexity are in the use of synergies and other actuated systems. First, synergies describe a combination of joint configurations and are traditionally used to simplify control mechanisms or to replicate complex hand behavior. They serve as a dimensionality reduction technique, mapping from a low degree of freedom to a high degree of freedom output space. According to Centello, 84% of hand variability can be explained just by the first principal components, a significant incentive to be implemented on robotic systems. However, implementing this into hardware has significant challenges. The author Catalano explores multiple common methods to drive robotic hands. Full actuation of each link is the most basic method, with software controlling the position of all links. These can be supplemented by adding more precise control systems, like variable stiffness actuation, at the cost of complexity. However, these methods are difficult to combine with differential or underactuated mechanisms, which improve grasp but need 3 degrees of freedom. Other approaches rely on hardware instead, embedding the behavior directly onto the mechanism rather than using software, achieving something known as rigid synergies. This can be further expanded with the underactuated components, resulting in our goal target, soft synergies, synergies with compliance, that can be understood as each joint in the hand being attracted to a target goal position. As for the implementation in hardware, systems with soft or adapted synergies tend to be highly effective for grasping, require minimal inputs and computation. The soft hand 1 and 2 and some of the RBO hands are popular examples. However, these also have limitations, as they tend to be bulky, require other external hardware for operation, or have a high mechanical complexity, making them difficult to afford and design. Thus, we rephrase the question in the motivation. Can we reduce mechanical complexity of these systems while still maintaining the desired behavior, the synergies? And to achieve this, of course, we propose to embed the synergies directly onto soft materials, rather than a complex mechanical mechanism. For our designs, we part from the bio-inspired soft finger proposed by Manti. The finger is comprised of a slab of casted silicon, with an inner tube to guide the tendon cable. The finger bends when the cable is under tension, and returns to its relaxed position by the stiff backbone material. Its bio-inspired structure is similar to human fingers in actuation, and the simple design offers some opportunities to customize its behavior. The design is, however, not very anthropomorphic, and will be modified before proceeding. As for the general methodology we followed, it is defined in 3 main sections. First corresponds to the design and calibration of a simulator. Using the finger we presented, we modify it, and we do experiments to calibrate it and obtain a digital twin. Next is the optimization procedure, in which we apply the synergies to these fingers. And finally, we construct the hand and do some experiments. The first step in the finger simulation was initial prototyping, in which, based on the original Manti finger design, we modified it adding a missing phalange and streamlining the fabrication process. The modified finger was then characterized. A setup was constructed where the finger was fixed and a tension applied at fixed intervals. Photos were taken, and machine vision techniques used to derive individual joint angles and cable displacement for each input. An identical setup was replicated in simulation using software simulation software and the Soft Robotics Toolkit package. Finger material was characterized independently to ensure parity with the real world. A script track selected vertices and essentially replicates the same process as when their physical setup. The following screenshots show real and in simulation finger position for a given cable displacement input. While some differences appear, behavior largely corresponds. The plot shows the average response for all tests, with the forwards and backwards trajectory of the finger having some differences, pointing to hysteresis playing a significant role. Simulation results are shown in green and are always bounded by the forwards and backwards behavior of the finger. Behavior can be assumed as quasi-linear until the end angles when the finger collapses or closes are achieved. While not perfect, the results do validate the simulation accuracy, particularly for small angles. For the second step, we move on to optimizing the validated simulation and achieve the desired behavior for all the fingers. To achieve synergies, we focus on the relationship between joint movements in a single finger, which can be related by several constants. For the end finger design, we identify some parameters that are likely to influence movement. In particular, we propose to manipulate the different thicknesses that we can see of the plates and hinges to modify the quasi-linear behavior identified before. Thus, by tuning the parameters, we can manipulate the movement relationship between joints, and thus move from a generic synergy into a smartly selected human synergy. For the semi-automated optimization process, we first identify all the fixed parameters to apply. These cover anatomical data, hand proportions, natural limits for the joints, and the desired synergy information across different movement planes. All this data was derived from literature. Additionally, we use control tuning parameters found described previously, which will control the application of the actual synergy. The properties are used to modify the base geometry, reused in the calibrated simulation environment. From here, the characterization experiment can be run, and new constant values can be obtained. If the obtained constant values are now below an error threshold with respect to the target values, the control parameters are tweaked again and the experiment rerun. Tweaking can be then performed several times, similar to a binary search. Once all fingers have reached convergence in simulation, we manufacture and repeat the original characterization process. Results of 4 fingers are shown. As in a particular example, the ring and the small finger are identical. Results here are also shown normalized respect to the fingertips. All except for one case are constrained to our previously defined 10% error condition, essentially validating our results. For the last step, we designed the hardware to hold the fingers. As a design tool, the Soft Robotics toolbox was used to fine-tune the position of each finger and adjust the relative potentials. Simulation results are shown on screen. This also ensures inter-finger consistency, as optimization was performed on each finger individually, rather than in group. Finally, we can move and design our soft hand, comprised of an acrylic base holding 3D printed supports with the silicone fingers. A tensioner box is used to adjust the tension of each individual tendon cable. By pulling from it, all the fingers move at the same time, actuated and are able to grasp different items. 2 tests were performed to study the capabilities of the finished hand. The first one was based on a modified version of the YCB gripper assessment dataset, with some additional objects of liking drawn in, a soft plush, and an oversized item. Overall, the hand was able to pick 16 of the 20 items presented. The second one was a simple force test, where the hand pulled a testing probe until failure. It was tested in two directions, distally and radially. It performed significantly better on the former. Contributions. On this presentation, we presented a method for embedding mechanical synergies into software structures. The simulation approach can be extended to more irregular assemblies and has the opportunity to be validated before construction in an interactive simulation. We also presented a soft gripper with an embedded soft synergy. The device is able to convert a very simple 1 degree of freedom input into a complex 15 degree of freedom output, and it's also very low cost. Finally, as for future works, it is of particular interest to explore embedding multiple synergies, as the silicon structure implies a very small increase in complexity, just adding more channels, but obtaining very complex results. Other projects include reducing hysteresis and thus improving response, and finally improving or working on the appearance, particularly in the context of prosthetic applications. And finally, this concludes our presentation. We would like to thank AIM2022 for their consideration, and it will be a pleasure to answer more questions.